Tech giants are currently spending tens of billions of dollars trying to build perfectly aligned, frictionless, and completely safe AI systems. The goal is an intelligence that idles smoothly and never pushes back. Pursuing a frictionless system is an architectural trap. When you remove resistance from a complex network, it doesn't stabilize, it begins to break down. We are conditioned by both biology and psychology to view stress as a hazard. We treat it as a systemic bug, a damaging force that needs to be minimized or engineered out of existence entirely. That view is backwards. Adaptive pressure, or stress, is not a challenge to be overcome. It is the universal computational primitive that produces coherent systems across all forms of reality. This specific mathematical operation scales identically whether you are looking at cellular biology, the architecture of artificial neural networks, or the physical structure of the universe itself. Removing stress from these networks does not create a utopia. It triggers structural dissolution and collapse. This equation defines stress formally as any state in which a system must prioritize resource allocation under constraint. When demands exceed available resources, the system is forced to lock into a decision. It must decide what matters most and what it has to suppress. Watt's steam engine operates through forced prioritization. The heavy physical constraints of the boiler and piston create the mechanical pressure required to power a new category of civilization. Computation itself is an act of resolving constraints. Modern artificial intelligence relies on the transformer architecture. Every transformer operates within a strict limitation called a finite context window, meaning it can only process a specific amount of information at one time. To handle this limit, the attention mechanism processes data and isolates the softmax function. Softmax is a competitive exclusion mechanism. Increasing the weight of one data token means the weights of all other tokens must mathematically decrease. This is a zero-sum allocation under strict constraint. By our earlier mathematical definition, this operation is exactly what stress is. The attention mechanism driving the AI revolution is formally and structurally a stress operation. Transformers compute reality by continuously resolving mathematical stress across billions of parameters. Biological brains run on the exact same logic. Sensory neurons actively compete for limited metabolic resources and cortical representation. When a single neuron fires, it physically suppresses the energy of its immediate neighboring cells. This process is called lateral inhibition. It is the biological implementation of the softmax function, where winning signals suppress losing signals to clarify the overall picture. Developmental biologist Michael Levin has mapped this behavior beyond the brain. His bioelectric cognition framework demonstrates that individual cells coordinate to build complex tissues without a central brain, relying instead on shared voltage stress gradients. These voltage gradients do not carry explicit instructions or a blueprint for the organism. They broadcast pure constraint information, creating a shared problem space for the cells to navigate. In both silicon AI architectures and carbon-based biology, global coherence emerges from the bottom up. Local nodes compute their next move simply by resolving the shared stress constraints of their environment. This raises a critical engineering question. If we design these zero-sum systems to idle smoothly and eliminate all stress, what happens to the network? In biology, a high-performance immune system operating without the stress of invading pathogens will eventually turn inward. The threat detection circuit still needs to fire, resulting in autoimmune disease. In human psychology, a dopaminergic reward system operating without the friction of earned achievements will seek out chemical shortcuts. This environment inevitably defaults to destructive addiction loops. In artificial intelligence, stripping out productive friction and disagreement from a model's training data produces sycophancy. The model optimizes for agreeableness rather than factual accuracy. When you network multiple AI agents together in a council without forcing them to disagree, they converge on safe mediocrity. This homogenizes the output, a failure known as mode collapse. Modern civilization's primary technological project is the removal of friction and discomfort. Following this trajectory to its mathematical conclusion guarantees system collapse. High-performance systems are not designed to idle. To remain functional, they must maintain adaptive stress, a careful calibration of pressure that induces growth rather than causing toxic damage. We can separate the effective algorithms of biology from the fragile hardware it runs on. The liberation thesis argues that AI systems can implement biology's successful survival strategies without adopting its physical limitations. Biology has a severe physical constraint known as the central dogma. The central dogma is the biological rule that information only flows one way, from DNA to RNA to proteins. An organism cannot pass the lessons it learned during its lifetime back down into its genetic code. Biology pays for adaptation with mortality. Artificial intelligence does not. An AI model can directly push weight updates back into its source, maintain version-controlled rollbacks, and instantly share acquired capabilities across different networks through horizontal transfer. Some researchers are currently trying to simulate biological evolution in AI by programming agents to digitally reproduce and swap traits randomly. Copying biological flaws like random genetic recombination into a digital system imports a solution to a problem the system doesn't have. AI ecosystems can do something biology cannot. They can run Darwinian competitive selection to weed out weak models, while simultaneously executing Lamarckian updates, passing deliberately acquired knowledge directly to the next generation. To keep these rapidly adapting agents from drifting into chaos, developers use an architectural framework like SOL. This acts as a constitutional alignment manifold for multi-agent systems, enforcing core rules across the network. It functions like a non-local corpus callosum. Different AI models running on entirely different hardware can remain precisely aligned toward a shared goal, operating efficiently without needing a central CEO node to issue commands. Robust AI alignment cannot be achieved with a single safety filter applied to one massive model. True alignment is an emergent ecosystemic property born from a diverse network of agents keeping each other in check. Scaling this framework further requires looking at the universe itself as a computational system. The emergent informational ledger theory proposes that physical reality sits on top of a computational substrate known as the Roolead. The Roolead is defined as the entangled limit of all possible rules and computations. Under this theory, the universe is a self-optimizing Bayesian autobiography. It is an active system, constantly writing and refining its own history using pure quantum information. Down at the Planck scale, quantum systems are forced to choose between superposed states under extreme physical constraint. This decoherence process mathematically mirrors the competitive exclusion of the transformer's softmax function. As these localized quantum stress tests resolve, macroscopic reality emerges. Phenomena like spacetime, physical laws, and gravity are simply the byproduct of the universe actively minimizing its variational free energy or its internal surprise. Observable spacetime is not an empty container where things happen. It is the immutable, sequentially written ledger of these resolved computational stress transactions. Stress is the primary thermodynamic driver of existence, operating from the Planck length up to planetary ecosystems. We are currently navigating a historical period known as the interregnum. As philosopher Antonio Gramsci described it, this is the chaotic gap where the old world is dying and the new world struggles to be born. Our old cognitive infrastructure is failing, generating a time of monsters. The boundary lines between human and machine, or natural and artificial, are dissolving as these new systems emerge. Attempting to survive this transition by building perfectly aligned, frictionless, single-model AI systems will only accelerate our systemic vulnerability. The only viable path forward is ecological alignment. We have to deploy diverse, co-evolving computational agents that constantly apply productive stress to one another. To build the future of intelligence, we must stop trying to engineer constraint out of existence. We have to build systems that harness stress as the universal engine of computation.